All right, so now we're on the last section of equilibrium. And as you can see, it's 7.13, where we're dealing with pH and solubility and how that those two things can be related. So again, a little bit of acid-base, and next unit we're going to get a lot of bit of acid-base, because that is the topic of our next unit. So this will serve as partially an introduction into this. So what we're going to look at, and we'll break this into two chunks again. You can start looking at the problems, but we just have this, looks like one, maybe two short lectures for the first part of this. And then, as a matter of fact, I'm going to hold myself to one lecture. There you go. And then we'll be able to finish that up on the second day. So this will be over 2 days, and I'll post the answers again at the end of the second day on this. But let's kind of go through this. I remember a few years back, this was the very first question. You had to know what KW was in order to do just about anything on the first question. And I kind of felt bad about not emphasizing that enough. But if you look here, water can actually be an acid and a base. It auto-ionizes to a very small degree, to the tune of 1 times 10 to the minus 7th for the hydronium ion or hydrogen ion. We'll use those interchangeably. And 1.0 times 10 to the minus 7th. And that would be your concentration of the hydrogen ion. Now, they are missing the units on here, so you should add that. Add the capital M. That's what they're referring to. So capital M, moles per liter. So real low concentrations, but if you're looking at this going, hey, 7, add that up, it's 14. Look down here, 14-point scale on pH, neutral pH solution 7, not a coincidence, okay? So this is kind of how that whole thing began here. But it's very important that you be able to look at this as an equilibrium system. And here we add yet another KEQ value, KW, which is the value for water. And of course, water is a liquid, so nothing on the bottom. It's a lot like a KSP, but it's a special version where a liquid can break up into and auto-ionize into constituent ions there. Okay, those are both the same. You multiply those together, you add the coefficients to get 1.0 times 10 to the minus 14th. That's the KW for water at 25 degrees Celsius. All right, so that's a real small one, which means, here you go, here's the brilliant statement of the day. Water is mostly water, but not all water, because there are some ions in it. So even if you have pure water, there will be some hydrogen ions and OH minus ions, hydroxide ions. So the hydrogen ions quickly jump onto a water molecule and make that H3O plus. So really commit that to memory. This is just sort of repeating what we just said. It is a given constant. Memorize this constant. I'm sorry, it's got 3 exclamation points. Memorize this constant. It is very useful. I have to shout that with the exclamation points. If you know the concentration of one, you can find the other, and vice versa. All right? So that can be very useful, because if you're given this, you know what KW is, then you can figure that out at the given temperature. Okay, so this pH scale, we talked about this before on a very recent slide, but keep this in mind. As you're sliding down the pH scale, low pHs have lots of H3O+, lots of hydronium, whereas toward the top, you get more and more OH-. All right? So, you think of these things as solutions and moving toward one side or the other. Now, this, excuse me, next few examples turned out to be kind of interesting little puzzles that some of the early chemists had. They're like, take something that didn't seem to be an acid and it didn't seem to be a base, like a salt, like NH4NO3, doesn't really meet our definition of being an acid or a base. And it was kind of mysterious to them as to why when I took a salt and dissolved it in water, why that would change the pH. As a matter of fact, the pH dropped. So here's something that you're like, yeah, that's NH4. You could consider that being a conjugate acid, and that's how it's acting right here, actually. The NH4 plus can donate that hydrogen to the water, so you've got acid, base, and now we have a conjugate base over here, which can now accept the proton, and then this of course is a nice strong conjugate acid, enough to change the pH of the solution. This drives enough that it's noticeable, and that was kind of a mystery. And then they started looking at all kinds of salt in their pH values, and they noticed that there's many instances where this can happen, and that's what this is kind of getting to. You're not truly adding an acid or a base to the solution, but these things are changing the pH. What about something like this? This one was really interesting when they first started studying this. Monatomic cations can release protons from the H2O. Okay? Cations attract the negative poles of the water, and then the positively charged cation decreases the electron density on the OH bonds, and some of the H plus then can break free. Okay? So, for a moment, you could have that OH and H compound. But if you look here, this is kind of interesting. So here is iron chloride, which is just a salt, and it kind of becomes this complex ion. This would be a good one to just know, because you're a brilliant AP chemistry student, and you know that an iron +3 ion makes a complex ion with 6 water molecules. And if you're interested in this stuff, you can look up, and it's an interesting structure of how those 6 water molecules make a complex. But we think of this as being sort of a polyatomic ion. So this, right away, complexes with those hydrogen ions. It's very similar to, like we talk about how salt gets surrounded by water molecules, but this is in a very predictable ratio and pattern, almost like it's starting to be its own sort of crystalline network, but in an aqueous solution. So here's your complex ion right here, and what will happen to it is one of those 6 water molecules you see here breaks out and becomes an OH minus. Okay? That's what we talked about can happen up here through those steps. So when it's OH minus, the negative charge drops this down, and the reason it became an OH minus is one of those hydrogens, again up here, could break free. Well, wouldn't you know it, if you have those extra hydrogens, that's going to drop the pH. So here's a metallic ion, iron plus 3, that just by adding it to water changes the pH. And that is something that you just need to know. It's a really unique thing going on here, but I think easy to understand, but also easy to forget. So make sure that you kind of understand these complex ions and some of the things that they do here. Okay, now here's and more examples of cations acidifying solution. The ability to release protons from water will increase as the ionic radius decreases. Okay, so the smaller ions will have the stronger ability. And of course, as the charge increases. So in other words, because of that statement, iron plus 3 decreases the pH more than iron plus 2. Iron plus 2 just doesn't have that ability to form that beautiful little complex with the 6 water molecules. And then also, Fe plus 3 is smaller with more net positive charges. Okay? So, this next statement, conjugate acids of strong bases will not affect the pH. So if we're looking at cations, you remember the bases that we picked out was you just drop down group 1A, and then we said CBS was the weird way I remembered that, but calcium, strontium, and barium. So those ions will tend not to affect the pH because they're relatively large, or that they have small net charges on them. You know, there's kind of a combination of those things. Plus 1 obviously is a small charge. That's about as small of a positive charge as you can get. So the plus 2, the ones that are bigger, because they're farther down, will also fall into that range. So it's sometimes easier to with figuring out which ones will change the pH by just looking at the ones that will not, which if you know your strong bases, which you must, then you know that. Okay? And anions can make solutions basic. All right? So anions of weak acids will accept a proton from the water, producing that OH, but the conjugate bases of strong acid will not. Okay? So again, know your strong acids, and these guys will not do that. However, something like your acetate ion could react with a water molecule to pull that hydrogen off so that the OH is available. There's more OH, therefore increasing the pH. Okay, so that's an example of that. The sulfate ion actually acts as a very weak base. Ka is an equilibrium constant for an acid, and so SO4 is a very weak base. What will happen is this will accept a few hydrogens enough to change the pH in a very small amount. So sulfate ion is just one of those sort of unique examples that work as well. Okay, I think we'll stop right there. This is a little more complex, and I promised just one lecture. So the thing you're starting to learn is that you can change the pH with these different things. The next one coming up are the metal oxides, and then we're going to take a look at weak acids and weak bases and what happens with those things in solutions as well, moving forward in this lecture. So start piddling around with those problems, get caught up on everything else. We're 1 or 2 lectures away from being done. Yay!